Okay, so on to the laws of thermodynamics. So chemical thermodynamics, this is linked to equilibrium. So equilibrium, we saw that we can have product favored, reactant favored. We have this, some kind of energy associated with it. So now we're going to look at why things actually go one way or the other, why they proceed in one direction towards equilibrium, and why equilibrium is kind of established as kind of the median point, right? So if I start out with all products or all reactants, we know it always descends on somewhere in between being the equilibrium. So we're going to talk about the laws of thermodynamics. I'm going to throw a couple equations. We've already looked at some of this, so I'm going to kind of work my way through rather quickly. I hope not too quickly, but I guess we're going to find out. So let's start with the first law of thermodynamics. First law of thermodynamics, energy cannot be created or destroyed, and total energy of the universe is constant. Basically, this says energy can't be created or destroyed. It just changes what form that it is. So energy cannot create or destroyed. Total energy of the universe is constant. And we'll talk about what the universe is, but ultimately the universe is everything. So surroundings and system together, that counts as kind of the universe. So the law of thermodynamics, so the first law of thermodynamics, law of conservation of energy, is usually denoted with the equation delta E, so total change in energy, is equal to Q plus W, where Q we know is going to be heat, and we know W is going to be work. And so we've already seen heat and work a little bit. Now we're going to look at it in a little more detail. So there we go, heat and work. That is the law of conservation of energy in a nutshell, in a simple equation. So let's just talk about that idea of total energy. So E total, the total energy of a system, is equal to three things. You're going to have the total kinetic energy of the system, plus you're going to have any potential energy of the system, plus you're going to have something that we're going to use U. Sometimes it's E, but the U is going to be our internal energy. So internal energy of the system. So internal energy, we're going to talk about it and then we're going to kind of ignore it at this point, but the internal energy of a system is the total internal energy kind of depends on all of the states of matter and the types of particles and the number of particles. So it's basically the chemical makeup and kind of the energy locked away within bonds and those types of things. So the total internal energy depends on all the chemical factors. So it depends on the temperature, it depends on the type of molecule, okay? So type of particle, let's say. It's going to depend on the number of particles and all of the other factors that might go into play that are chemically related. Okay. So back to the original. So we're going to kind of ignore internal energy, but it's kind of included in that total energy that's present. So back to this idea of energy is heat plus work. So heat and work, those are two different types of energy. And this is kind of where the total energy can't be created or destroyed. It has to be transferred. So we have this system over here to the right. So first of all, work is the process of transferring energy. So I have my little drink here. By lifting it up or moving it left to right, that is me moving mass. Anytime you move mass, you are performing work. So work is the process of transferring energy. And this sentence kind of finishes with to an object. So work is the process of transferring energy to an object. So we know work is equal to negative P delta V when we're looking at the movement, the transfer, the movement of matter. Okay, so we're looking at changes in volume, because a change in volume, for example, over here, we might see the expansion of this, the pushing against this piston is basically moving that mass. So here's the mass. By expanding the volume, we are doing work on those surroundings. So we have work, okay? And so if I push this, if I expand the volume within this, if I increase the volume, think about that. By increasing this delta, we are increasing the negative work term. So that would be a negative work term. If I am decreasing the volume or the weight is pushing down and creating less volume, that is a positive work term. Okay, so one more time, just simply a positive delta V is equal to negative work, and a negative delta V is equal to positive work. Okay. Again, I'm going to say this just quickly, and you can write down if you want to. Negative work term is the system doing work on the surroundings. Okay, so it's performing work on the surrounding. It's pushing against the surroundings. A positive work term is doing work on the system from the surroundings, or work is being done on the system or by the system. So work is being done by the system would be negative. Work would be on the system is going to be positive. So a matter transfer. So first of all, this idea of matter transfer, again, moving matter counts as doing work. This can only occur in an open system. We use open systems all the time in chemistry, right? If we're running a reaction, we have an open vessel, the gas molecules can evaporate. Gas molecules evaporating, that's an open system. It allows the transfer of matter. Okay, so for heat flow, so this is the work term that we're going to use, and we're going to come back to this. We're going to kind of isolate this and put it into one thing. I'll never talk about work other than looking at pressure and volume changes, but we're going to kind of put this all into one equation, one final equation in all this. So this is kind of the development of all of that. So in terms of heat flow, so we've talked about heat already. Q is simply equal to delta H, or the change in enthalpy, because delta H we know is enthalpy. So I'm just going to highlight this. Q is equal to delta H. Heat always flows. So if I have a system and I have the surroundings, in fact, I can probably just do that above, actually. If I have the system and I have surroundings, what I know is if heat flows out of the system into the surroundings, so out of the system and into the surroundings, this is going to be a negative Q term. The flow of heat is kind of what we're looking at. The change in heat is going to be hot to cold, but we're always going to see that change. So this is a positive Q from system to surroundings. So heat is released by the system, heat is absorbed by the system. So positive versus negative. Okay, so let me just put that into context quickly. Again, if heat is absorbed by the system, this is very system-centric look, okay? That is a positive Q where things go from the surroundings to the system. And then if heat is released by the system, that is a negative Q where we're looking at things going from the system to the surroundings. Okay, all right. So let's kind of put that together. So I have delta E is equal to Q plus W. And now I can plug in the two terms that I have. So delta E is equal to, we know Q is now delta H. And I know that the work term is now minus P delta V. So there we've got a new change in energy with things that are more practical, right? I can calculate enthalpies, I can look at pressures, I can look at change in volumes. So these things are all state functions that I can adjust. So all energy, pressure, volume, and delta H in this context are all state functions. So I care about final and initial values, and that's really what we're looking at. So let's kind of look at this system right here. So a couple of things. So what we're seeing is this reaction of HCl and zinc. So HCl plus zinc is creating H2 gas plus zinc chloride. Okay, zinc chloride aqueous. And so we're getting a couple of things. In this case, this is a closed system. If I were to look at my change in energy Q plus W, is my Q positive or negative? Well, we see that heat is leaving the system, so it's released by the system. That would be a negative Q, right? So we could say not the work term, the heat term is going to be negative. What about the work term? In this case, I'm pushing back against the surroundings, so I'm increasing the volume. A positive delta N is a plus or a negative work term as well. So overall, my total energy for this is going to be negative, and the system is losing, system is losing that energy. It's kind of pushing back against the, it's losing it into the surroundings because it's pushing back against everything, right? So that concept, those are the concepts that we're looking at, the change, overall change in energy. So we need to think about this in terms of spontaneous processes. So we have these releases of energy, but why do these things even happen to begin with? So we're going to talk about the idea of a spontaneous process. What is a spontaneous process? Well, a spontaneous process is a physical or chemical change that occurs by itself. What do I mean by itself? Well, what I mean is something that is spontaneously going to happen with no outside force or influence. So no outside force is required. It's just all of a sudden going to start to spontaneously do its thing, okay? And it continues until equilibrium is established. So we think of things like spontaneous combustion. These things happen, something's going to catch fire and it's going to burn until it has essentially turned everything into ash, because that is the equilibrium system, that is the equilibrium state for things to be in. If we think about a hill, let's say, with a ball on top of it, the spontaneous thing for this ball to do is going to roll down the hill. That is the spontaneous process of that thing rolling down the hill, okay? When it's down here in its final state, if I wanted to return it back to the top of the hill, that is what we would call a non-spontaneous process. So that is a non-spontaneous process bringing it back up the hill, as in it's not spontaneously going to roll right back up the hill. So spontaneous process is something that is going to occur. Returning it to its position is generally non-spontaneous. So if it's spontaneous in one direction, generally it's non-spontaneous in the other. So let's take a look at a couple more examples of that. So if I take a look at at two cylinders that are connected by a stopcock. So here I have a stopcock in the middle, and we have these two cylinders, okay? So we'll call this, I'm going to create two of these. We're going to do a before and we're going to do an after. So if I happen to put a bunch of gas molecules in one side, okay, so I've got a bunch of gas molecules in this side here, they're filling up the whole space up to the stopcock. So we have side A, we have side B. Side A happens to have 1 atmosphere of pressure. Let's just say to make life easy. And the right side is just vacuum. It has been evacuated. Okay, so there's nothing there. If I open that stopcock, what do we expect to happen? Well, if we open that stopcock, we double the volume. By doubling the volume, we expect the gas to fill both chambers, and therefore we expect to have half an atmosphere in both, right? So if this is B, this is A. That's spontaneously going to happen, right? All the gas molecules are not going to stay on that side. They're going to spread out. They're going to do what gas molecules do, and they're going to take up the space that they have. So this is a spontaneous process. All right. Is it possible to return back to the original state? Well, if it is, and it absolutely is, it would be through a non-spontaneous process, as in magically, we're not going to end up with a situation where all of those gas molecules just end up on the other side, right? So this is the equilibrium position In order to go back to a non-spontaneous position, we need everything to be piled up on the side. Well, we could actually submerge this whole side in liquid nitrogen. All of the gas would become liquid. When it becomes liquid, we simply close the stopcock and then we push it back in that direction, let the thing reach room temperature again, and boom, you have everything on one side and the other side is evacuated. So it is possible, but we had to put energy in. Having to put energy in is what defines something as a non-spontaneous process. Spontaneous is just going to occur. Again, we start in a position with a bunch of reactants, we know it's going to shift to equilibrium because that's a spontaneous process. So the aspects of a spontaneous process, things that we don't really think about, but are true of a spontaneous process. So particularly when it comes to phase changes. Okay, so first of all, pressure and temperature do play a role in spontaneity. It's a weird word to spell, spontaneity. Okay, so if we think about ice melting, if I have ice below 0 degrees, it is spontaneously going to be a solid. It's not all of a sudden going to turn into a liquid. If it's above 0 degrees Celsius, it's spontaneously going to turn into a liquid, right? So we're not going to expect things to just freeze above 0, or water to freeze above 0, because that's a non-spontaneous. I would have to do something in order to make that happen, increase the pressure, decrease the temperature, do something to take energy out of the system in order to force it to freeze. Okay, so a process that is spontaneous, this process that's spontaneous in one direction, or I guess I should say at one temperature, may be non-spontaneous, may not be at another. So just because it's spontaneous at one temperature doesn't necessarily mean it's going to be spontaneous at another. So for example, again, using this one, above 0 degrees Celsius, ice is going to spontaneously turn into water. But below 0 degrees Celsius, we expect ice to return to the typical state that we're going to have. So temperature does play a role as well as pressure. If you think about things like those pressure temperature diagrams we had for phase, right? So if I change the pressure and the temperature, we're going to see things spontaneously become whatever phase we say they're going to be in, right? Spontaneously, it's going to become diamond or graphite or something like that. So the reversible process of all of this. So systems change. So the idea behind, there's two types of processes, a reversible process and an irreversible process. The world is made up of all sorts of reversible processes, okay, and irreversible processes. But there's something special about these. So let me just, not to bury the lead, equilibrium is a reversible process. It is, there's no energy involved. It's spontaneous in both directions at equilibrium. So a reversible process, system changes in such a way that it is that the surroundings in the system and surroundings can, with no outside effort, be put back in their original position by exactly reversing. That's important. By exactly reversing. So nothing can change. You have to reverse it exactly reversing the process. Okay, so if I have the system and I have the surroundings outside of it, so ultimately what this means is there is no net change to the system or the surroundings. Essentially, you cannot, ultimately what this means, and we're going to see this in a second, is you cannot increase entropy. I can't add more randomness. I can't distribute energy anymore. We are, or ultimately what this really means is we're at equilibrium. Okay, there's very few reversible processes. A frictionless surface or a resistanceless wire, those are reversible processes. But the world is made up of irreversible processes. So here I have a partition. I lift this up and I do work and I decompress this or I compress it again. This right here is a irreversible process because I didn't exactly reverse it. I didn't put the partition down and all of a sudden everything ended up on the other side. Ultimately, work done by the system is equal to 0 to start. All right, that's irreversible expansion of a gas. Work done on the system is greater than 0 because I have to put work in order to compress it again. So ultimately, we've gone from this state of the original state to the final state, although they're the same, they weren't exactly reversed. Okay, so work done by the system is equal to 0. Work done on the system is greater than 0. So ultimately, we've had to do work in order to return it to its original state. So what does all this mean? Again, an irreversible process cannot be undone. By exactly reversing. A change to the system. Okay. And any spontaneous process. When I say process, I'm including everything in that, including reactions. Any spontaneous process is irreversible. So ultimately what that really means is we're at a Q, we're at some state that's not equilibrium. Any spontaneous process is irreversible because we would have to do work in order to get it away. And again, non-spontaneous process can only occur if the surroundings do work on the system. Again, we're always trying to climb towards equilibrium. Once we reach equilibrium, in order to go back away from equilibrium, we have to put effort in. Okay, so this is all leading to something. So non-spontaneous process can only occur if the surroundings do work on the system. So what does all this mean? What this means is the world is filled with all of these irreversible processes that ultimately cannot be undone, right? We have to put work in. What that means is the world is ever changing. Every single moment we are increasing the randomness, or we're changing to a state where we've run through our irreversible processes. We have a limited amount of energy, as the first law of thermodynamics says. We are using that energy in order to go to equilibrium, everything go to equilibrium. And at some point, we're going to reach the state where we have reached equilibrium everywhere. And we are essentially, it's called the ultimate heat death of the universe, where everything is needs to be pushed in the other direction, but there's no energy to do it. So let's talk about the idea of entropy. Entropy is a really hard concept to understand. And in fact, I think I'm going to turn this off here and let's talk about entropy in the next video.